Okay, in this video we're going to look at question number 4, and part A says, suppose that a particle moves along a path described by the vector function r of t, and that the magnitude of r of t is constant for all t. Show that the position vector r of t and the velocity vector v of t are orthogonal for all t. Interpret your result. Okay, so our assumption here is that as we move along our path described by the vector function r of t, the magnitude of our position vector is constant for all t. Okay, so put another way, our distance from the origin is always the same as we move along our path. And so that implies in particular that the curve described by r of t lies on a sphere centered at the origin. Okay, so as we move along this blue path, the magnitude of our position vector, which is really just our distance from the origin, is always the same. Okay, so we're in fact moving along a curve that lies on a sphere centered at the origin, and the radius of the sphere is equal to this constant magnitude of our position vector. Okay, now our job is to show that in this instance, when we move along a curve that lies on a sphere centered at the origin, our velocity vector is always orthogonal to our position vector. Okay, so to prove this, we're going to show that r of t dotted with v of t is equal to 0 for all t. Okay, and to do that, go ahead and make a little space here. We're going to start out by letting this constant magnitude of our position vector equal capital R, where we've already noted capital R, that's just going to equal the radius of the sphere that our curve lies on. Okay, and so now go ahead and square both sides. Okay, so the magnitude of our position vector squared is equal to the square root of the sphere, the radius. And now we'll go ahead and use this property of dot products that says that if you take a vector and dot it with itself, that gives you the square of the magnitude of that vector. Okay, so now we have the fact that the dot product of r with itself is equal to the square of the radius of the sphere. Okay, now I want to get the velocity into this picture, right? Because we want to show that r dot v is equal to 0. So what I'm going to do now is differentiate both sides of this equation with respect to t. Okay, so if we do that, well, first note that since the square of the radius of the sphere, so capital R squared, is a constant, okay, this right-hand side, in fact, is 0. Okay, what about the left-hand side? Well, we can differentiate it using the product rule for dot products, okay, that we saw a while back. So this would give us r prime dot r plus r dot r prime. All right, now remembering that the dot product is commutative and r prime is just by definition the velocity vector, we now have the fact that 2 times r dot v is equal to 0. And so dividing both sides by 2 implies that r dot v is equal to 0. Okay, so as we move along this path that lies on the sphere centered at the origin, our velocity vector is always orthogonal to our position vector. Okay, great. So that does it for part A. So now let's go ahead and check out part B. Make some space here. All right, so now for part B, question says, suppose that r of t describes a smooth curve, meaning that the magnitude of the velocity, so in other words the speed, is non-zero for all t. Show that the derivative of the magnitude of the position vector with respect to time is equal to the scalar projection of the velocity vector onto the position vector, and then interpret the result. Okay, so unlike part A here, we now are allowing for the possibility that our distance from the origin changes as we move along our path, right? So in other words, our magnitude of this position vector, it can change. Okay, so our job is to show that the rate at which our distance from the origin changes with respect to t, that's what this derivative is telling us, is equal to the scalar projection of the velocity vector onto the position vector. Okay, so now first thing I want to point out here is that the scalar projection of V onto R is equal to, well, you got to go back to scalar projections, right? This is equal to the dot product of the two vectors, so R dot V, and then you divide by the magnitude of the vector you're projecting onto. Okay, so here we're projecting onto the vector R, so we're dividing by the magnitude of R. Okay, so our job really is to show that this derivative is equal to this expression here in white. Alright, so now we can proceed in much the same way we solve part A. Okay, I'm going to start out with the fact that the magnitude of R squared is equal to R dot R. And so I'll go ahead and differentiate both sides with respect to time. And now on the left hand side, since I'm differentiating this square, I'm going to go ahead and use the chain rule, right? So the chain rule says, okay, differentiate the square first. The 2 comes down and multiplies the inside, which is the magnitude of R. And then the chain rule says I have to multiply by the derivative of what's inside. So I have to multiply by the derivative of the magnitude of the position vector with respect to time. Okay, now on the right hand side, just like in part A, we're going to use the product rule for dot products, so that gives us R prime dot R plus R dot R prime. Okay, now I'm going to leave the left hand side alone for the moment and clean up the right hand side. So R prime is V, and the dot product is commutative, so I really have 2 times R dot V on the right hand side. Okay, now if we go ahead and divide both sides of this equation by 2 times the magnitude of R, we find that the derivative of the magnitude of R with respect to time is R dot V divided by the magnitude of R, which as we noted up here, is equal to the scalar projection of our velocity vector onto the position vector. And that's the end of the proof. Alright, very nice. So now let's go ahead and interpret the result. Okay, so as I've already said, right, the magnitude of our position vector is really our distance from the origin. And so this derivative here, right, that's really measuring the rate at which our distance from the origin changes. And what this result says that we just proved, right, it says that that rate at which our distance from the origin changes is equal to the scalar projection of V onto R. Now what does that measure? It's measuring the component of our velocity vector onto our position vector, right? So if I take the position vector and I just translate it up so its tail coincides with the tail of the velocity vector, okay, I can project V onto R, and that gives us this projection vector here in purple. And now the scalar projection, remember that's the sine magnitude of this purple projection vector. Okay, so this result really is saying that the rate at which we are moving away from the origin is equal to the extent at which the velocity vector points in the direction of our position. Okay, so the more that V aligns with the position vector, the faster we will move away from the origin. Okay, so with that in mind, let's look at 2 cases here. These are 2 rather extreme cases. I'm going to make a little space here. Okay, so first case is where the curve lies on a sphere. Okay, so this is really just part A. And there, right, since the magnitude of the position is constant, this derivative is just 0, right? Our distance from the origin actually never changes. And from part A, we prove there that R dot V is 0, so that implies that the scalar projection of V on R is equal to 0. Okay, so in this scenario, right, the velocity does not point in the direction of R at all, right? The component of V in the direction of R, in fact, is 0. And as a consequence of that, our distance from the origin never changes, and so we are stuck on this sphere centered at the origin. Okay, as another extreme case, we can consider the scenario where our curve is actually a line through the origin. Okay, so here, our position vector and our velocity vector are parallel to this line. Okay, and so here, V perfectly aligns with our position vector. So if I project v onto r, that's just going to give me v itself. And so this scalar projection is just going to tell me the magnitude of the velocity, which is just our speed. Okay, and if we're moving in the straight line path, right, and the line passes for the origin, okay, the rate at which we escape from the origin, right, the rate at which this distance from the origin grows, that then would also just equal the speed of our object, right? So these, again, are equal to one another. Okay, great. Well, that's a good place to stop, and I will see you in the next video. Thank you so much.